Hi, I'm Francesco Campanella.
Hey, I'm Conrad Koo.
Hi, I'm Peter Chen.
I'm Super Pat Warden.
Hi, I'm Steven.
Okay, so input power is scaled down from 60 RPM down to 30 RPM via a set of 2-to-1 bevel gears. These are both 3D printed. It's again scaled down to 10 RPM via a set of 3-to-1 spur gears, which are both acrylic and 3D printed again. We then have a 1-to-1 acrylic spur gear set here, which provides power to both the forward shaft and the reverse shaft. So we have two shifting mechanisms here and here, which are both the sets of dog clutches. For reverse gear here, we have a single-sided dog clutch that engages and disengages, which will power reverse the output shaft at 10 RPM. We again have two forward speeds here with a 2-to-1 pulley and 1-to-1 pulley, with a double-sided dog clutch, which will slot here to power 10 RPM slow, and again, power here for 20 RPM fast. These both output through pulleys to corresponding output pulleys on the output shaft, which will then drive and lift the weight in the bucket.
Here's a closer look at our dog clutch mechanism, which engages and disengages our reverse speed. As you can see here, we have our sliding dog clutch, which has this isolated lever in the middle that can spin freely, but also drag it back and forth along the axis. Here is a brake for the output shaft. And here's a closer look at our shaft supports for this side. As you can see, we made the profiles as large and beefy as possible to resist all the bending and torsional forces.
Yeah, so some of the first challenges that we ran into were that our supports weren't really sturdy enough to hold up to the loading during operation. And with our first generation of supports, you can see that it's just like a thin, like straight wall. And like we can see that we were trying to pin our shafts and it broke already at the top. And that our shaft holes were a bit too small to allow for bushings. So with our second iteration, we add some flanges along the side, and then we also added more material to go around the shaft. But this design couldn't really resist the torsion during operation, and it would twist, causing our gears to disengage. So after that, we converged to our final design, where we beefed up the supports with a lot more plastic material, and you can see that we added a lot more like flanges and like just flanges to bulk up our material. And yeah, this worked pretty well during operation. We didn't have any gear slippage.
Initially, for speed selection, we were planning on using a CVT. A CVT, or continuously variable transmission, operates on using a continuously variable gear ratio, which allows for switching between speeds. The issue with using that was we needed a single belt that was tensioned the entire time to prevent slipping of the belt when the gears were loaded. We found that instead, based for size constraints, we would use a double clutch system. Our initial design were these small spur gears, but using 3D printers, there was a lot of support material that would get printed in between the teeth. So we found we needed to file it down, and actually it could lose contact because of the depth of the teeth. So we moved on to using larger 3D printed gears with thicker face widths and larger teeth that allowed for more engagement. But because the 3D printed material wasn't very strong, it would slip on the shaft, and so we went to an acrylic laser cut part. And finally adjusted it to a smaller diameter to account for the spacing of the pulleys and the belts.
Yeah, so originally when we first 3D printed the parts and tried to slide them on the shaft, they would slip on the shaft. So to combat that, we had these, we laser cut these Y acrylic pieces that would be hot glued into each of the 3D parts. And then with that, we were able to reduce or even eliminate the slipping on the shafts for all of these components.
Oh yeah, so here's the part over here in the assembly in the light gray. Basically, this slides and catches on and allows the transition to the reverse speed. So the way we go about FEA is first you have to determine the maximum amount of force that's going to be placed on this dog clutch. And that force occurs when during the high speed forward, during liftoff, when the acceleration is the greatest. So we approximate the lifting as a velocity step response, and this is our equation estimate. So as you can see, the steady state is 0.33 feet per second, And this is our estimated time constant. And we basically take the derivative of this to find the maximum acceleration to be 1.3 feet per second squared right here. And from that, we can draw a free body diagram where then we find the acceleration. And here's also our gravity force. And from that, we can calculate our force of gravity is 8.8 pounds. Our force from that upwards maximum acceleration is 0.356 pounds. And then add those together, you get 9.7 pounds. And you divide that on the 5 teeth of the dog clutch to get 1.8 pounds per face of the dog clutch teeth. And here's a quick FTA using Fusion 360. As you can see, we apply forces on each of the faces. And from this, we see that the maximum stress based on the part is 1.17 megapascals. And based on the wheel strength of PLA plastic, the safety factor is around 153.32.